The next question is ChefProduct. Chef has a special interest in studying the set integers. So it defines n as a good set as a set of distinct non-negative integer, and the good set should satisfy the below two conditions. Sum of the elements of the set should be equal to n, and the product of elements should be odd. So we need to find the number of distinct sizes of good sets that can be formed with a given integer. So
yeah, let's see how we can solve this question. So this question is divided in two different cases. First case is if n is even. Okay. We'll cover n is odd later on. First, we'll cover n is even. Okay. Now, if n is even, what we are given in the question is that the product of all the numbers should be equal to a odd number, right? So if the product of all the numbers has to be equal to odd number, every single number in that we include has also should also be an odd number, right? And one more condition that is given is that the sum of all the integers in the set is equal to n, right? Now, if n is even, and we want the sum of all the integers in the set to be even, and all of those numbers are odd, so okay, basically there are some odd values we are adding, right? Right, and that has to be equals to n, right? Why we are adding odd? Because if we include an even, then the product will become even, right? So we need all odds on. So some set of odd numbers, and all these odd numbers are also distinct, right? So these distinct set of odd numbers have to be summed up to become an even number, right? And what is the condition for them to become an even number? The number of odds we use should be even, right? We cannot use 3 odds and achieve a even number as a sum, right? So I'll just write down the two conditions. Basically, all numbers included should be odd. Okay. And number of number of values should be even. Okay. So for n equals to even, these two conditions should satisfy. All the numbers included should be odd, and the number of values should be even. Okay. Now let's take a number. Now let's see. Now, since the number of values should be even, let's take some of the most basic cases, right? Now, if we have, let's say, I want to include two numbers. Okay, I'll take the smallest two numbers possible. So I can include 1 and 3. Since they have to be distinct, I need to take 1 and 3 only, right? And 1 and 3 both are odd. Okay, 1 and 3 will give a sum of 4, right? So can we say that any even number after 4 can include 1 and 3, right? We can include 1 and 3 in them, because 1 and 3 sums up to 4. So whatever that sums up to will always be something less than 4. So we can always include them, right? Now, if we take, let's say, 4 number instead of 2, let's take 4. Okay. So we have 1, 3, 5, and 7. This will give a sum of 16, right? Now we know that for any number between 4 and 16, now basically, if we are trying to include 4 numbers in the set, the value should be at least equal to 16, right? Because if we go below 16, then we can never achieve, we can never include 4 numbers to achieve a sum of that, right? So basically, all the numbers between 4 and 16, for them we can use 2 numbers, but we cannot use 4 numbers, right? Similarly, if we take 1 plus 3 plus 5 plus 7 plus 9 plus 11, this will give us 36. Okay. Now, if you observe a pattern here, we can observe a pattern here basically. This value is basically 2 square. This value is basically 4 square, this value is 6 square, right? So these are all the even numbers squared, right? So, and the number of sizes possible, right? So the number of sizes possible for numbers up till 4 will be equal to 2, it will be equal to 1 only, right? So, okay, basically, if a size is possible, if size of 4 is possible, then size of 2 is also possible. Basically, we can use numbers like 1 and 15. For let's say for 16, we can use numbers like 1 and 15, 3 and 13, and so on, right? So if 4 is possible, even 2 is possible. Now here, if you observe, the number of sizes for numbers up till 4 will be 1, okay? The number of sizes up till 16 will be 2, and the number of sizes up till 36 will be 3, right? So when I say up till 36, I mean from 16 to 36, from 4 to 16 and all, right? And we can use a simple formula to find this out. Given any even number n, we can just say square root of n by 2, okay? I'll just write by 2 here. Square root of n by 2. And this is basically floor division, right? So whatever number you get, you just round it off to the smallest number, biggest number closer to it, right? So this is okay. Basically, this is floor division, okay? And this will be the answer, right? So if we have 18, let's say, square root of 18 will be what? Somewhere between 4 point something, right?
Yeah.
And when we do by 2, it will give us 2, right? And if you observe, 18 is between 16 and 36, right? So 2 will basically apply to all the numbers from 16 to 36. And so we can confirm this formula, right? Okay. Now, let's see the case for odd numbers. Okay. Now we'll write if n is odd. Okay. Now, if n is odd, we know that the product of the numbers should be odd. So the first condition will always be true. Basically, all numbers should be odd. And another condition is, since it is odd, the number of numbers we include so should be odd, right? So the number of values is odd. Okay. In the previous case, the number of values we had to make it even, because only then a sum of even is achievable. If n is odd, the number of values have to be odd, only then a sum of odd is achievable. Okay. Now in this also we do the same thing. We'll run through some very basic cases. So we'll just include one single odd value, which is 1, which will give us a sum of 1. If we include 1 and 3 plus 5, so we are including basically 3 odd numbers here. It will give us a sum of 9. Okay. Now let's include 5 odd numbers. So 1 plus 3 plus 5 plus 7 plus 9. Okay. What will that give us? That will give us 25. Okay. Now if you observe, there is a similar pattern here. Okay. This is basically 1 square, 3 square, and 5 square. Okay. In the even case, we had all the even powers here. 2 square, 4 square, 6 square. Here we have all the odd powers here. 1 square, 3 square, 5 square, right? So from this, we can tell that all the numbers that will lie from 1 to 9 will have only one size, which is 1. All the numbers from 9 to 25 will have two sizes, which is 1 and 3. Okay. And similarly for 25, from 25 till next power of next odd power would be 49. So from 25 to 49, all numbers will have 3 different sizes, which is 1, 3, and 5, right? So yeah, in the similar way, we can solve this question as well. Basically, given n, where n is an odd number, what we do is we say square root of n, okay? And we'll add 1 to this, and we'll do by 2, okay? This is also again floor division, okay? So let's take a number like 11. Okay. Now for 11, what will be the square root? 3 point something, right? Plus 1 by 2. We take floor division, which will basically result in 2, right?
Yeah.
And we know from here that 9 lies between, 11 lies between 9 and 25, right? So for that, we'll have two different sizes, size of 3 and size of 1, right? So yeah, this is how we solve this question. And the time complexity of this question will be O of 1, okay? O of 1 because we just find square root and a simple formula to basically do division and all and print the answer, right? So yeah, this is how we solve the question. If you use binary search to find the square root, then it will be O of log n, basically. But yeah, this is how we solve the question.